Hi Dave, this is Jesse. I meant to do a write-up for you, and then it occurred to me as I kept procrastinating that the write-up would probably be more of a strain on you to take a look at than it would be to just make a little video that I'll park on the internet. And then I'll send you the link, and you can look at it at your own leisure, and hopefully when you're in recovery from your surgery and you want to have a giggle, you can take a gander. Anyhow, what I did was I opened up a bunch of different things down here on my bottom toolbar, if you will, to sort of get the ball rolling and figuring it out. This last one here is Snagit, which is a poor man's version of a video recorder. I'm going to start out by going over and taking a quick look at the original tracker idea that we were talking about. If you look at the left-hand side, we had a series of feedback shift registers, each driving an LED, and 10 bits was the original model, and there were going to be 32 channels, as I recall. Initial thinking was to use linear feedback shift registers that would be the ones that would give you full 1023 bits, but they would actually just be variations on each other. So, in other words, there's like only one or two polynomials that create these 10-bit things. So my thought process was the main thing is that each channel be unique. And so I thought, well, we could preload shift registers with distinct 10-bit patterns and have them circulate. Initially, we talked about having them all blasting their LEDs at once. Come back and talk about that a little bit later, but I'm currently of the mind that we might want to have them sequence. In other words, one guy blasts, and over here on the right-hand side, we receive it with the input receiver and take an A to D on it and run a correlation. And then the next guy blasts, and we walk through all 32 of these and then go back to the top. So it would be continuously circulating, but unique. We can go either way. But as we start looking at the kind of data that we're going to be getting, we might want to consider some options. Anyway, the target, what we're going after, as I understand it, is to figure out the distance between the LED and where the receiver is. And so if these guys were slanted or something like that, you'd see that this one might be closer, then that one might be a little further away, and that one might be the furthest away. Remember, there's 32 of them. Anyhow, so that was sort of the picture of where we got started. Now, I remember the summation and looking at the particular approach that SMath had of taking a correlation, but I got into looking at the internet a bit, so I'm going to close this and show you one that came across and struck me. This is actually, I think he's probably Indian from his speech pattern. But he does a quick look at both convolution and correlation that were very straightforward. I'm going to play both of them, and hopefully I can get that down. I want to play both of them. That would be this one. And I'm going to hit go on this. He actually has this duplicate, so I'm going to try and just play it from beginning to end.
Hello and welcome. We are going to show you a simple method to calculate discrete convolution and correlation. Let's start with convolution and take the following example. Find the convolution between x and h, or find y for the system shown below, where x has the values of 1, 2, and 3, h has the values of 4 and 5. First of all, we arrange the elements of x vertically and the elements of h horizontally and perform multiplication as shown in this table. Now we perform addition according to the red arrows. So 4, 5 plus 8 is 13, 10 plus 12 is 22, and 15. So the result of convolution between x and h is 4, 13, 22, and 15. Now let's take another example to calculate correlation between x and h, where x has the values of 1, 2, and 3, h has the values of 4, 5, and 6. First of all, we arrange the elements of x vertically and the elements of h horizontally and perform multiplication. Now we perform addition according to the red arrows. So 6, 5 plus 12 is 17, 4 plus 10 plus 18 is 32, 8 plus 15 is 23, and 12. So the result of correlation between x and h is 6, 17, 32, 23, and 12. Thank you very much.
Okay, now if you look at this, you can see where the link is on that if you want to find it, or I can send you that. Anyway,
I think I have a solution.
I'm done with that. So I got to thinking about it, and I took his idea, which sort of appealed to me, and I remember that because you don't do a flipping with the correlation, I figured where you had x and where you had h probably didn't matter. And what I did was I sat down and I did some spreadsheets. And I'm going to show you 3 of them. And I thought I had these. Yeah, okay, this is the first one. The first one is going to be a monotonic one, and then there's going to be a matching one, and then there's going to be a uniform one. And what I mean by that is the following. The column A here is going to be what I'm calling the target. In other words, that's the known pattern that we're looking for. And you'll recall that we discussed, I think it's called a matched filter. And what you're doing there is where you have a 1 and a 0, you actually substitute a -1 for the zeros. And so this is showing you an alternating pattern of 1, -1, 1, -1, which stands for 10, 10, 10, 10, 10, all the way down. And so this is my target, the thing I'm looking for. Up here are a series in this top row here of incrementally increasing monotonic values. And what I'm doing is I've kind of got it screwed up because I've got things a little bit shifted in terms of below that top row. But in this area here, I've done a multiplication of the top row by the first element on the left, and then the top row by the next element on the left, etc., going all the way down. And in the same sense that the Indian guy from the previous one was doing things, I have, let's see, ignore this particular column, but this is going to be corresponding to that value. 1 and -2 is going to give you that one. -1, 2, and -3 is going to give you this one, etc. So the coefficients or the correlation values are these guys going along the bottom, and then they should go up to the top but skip the guy at the very top. This one here, this -5, is of interest to me because it's like the value of the diagonal sum. So the diagonal here is an interesting point because, or it's an interesting factor because it's the only calculation that actually involves all the elements of both the top row and the left column. Notice that this is going to give me, if I have 10 by 10, what I'm going to get is 19 values that are coming out of this. And 19 values for one channel, okay, that's cool. Now I have 32 channels, and I'll be looking at approximately 30 times 20 data values for scanning across all my channels, or 600, thereabouts. Anyway, that was a concern. So I just wanted to say here's sort of what it looks like if you have a monotonic input. I did another one down here, and I have a matching input. Now notice I'm doing matching where 1, 0, 1, 0 in this domain is regular ones and zeros. Over here in this domain where we're actually having the target, the negatives stand for subtracts and the positive ones stand for adds. And you get values that look like this coming out at the bottom. Again, the same procedure. Notice that in the case of this one, I'm getting like a 5 on my diagonal, okay? And for some reason, going up here, I think I ended up getting like all zeros. Excuse me. Now, So on this one, which is the uniform one, in other words, all the values are 5, and again, it's the -1. Oh, I screwed up here. Apparently I've got, I've got a different pattern, so I've got a different target on this one, sorry. I've got 5 -1s and 5 +1. So this would be 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. I should have kept the same target for these because it's a little less meaningful now. Again, though, the multiplication is across here, and then we do the adds down the diagonals. I just wanted to point out that the values come out and they're fairly consistent. But these are the sort of things that affected my thinking. I'm going to go back to this one for a minute. I said, I looked at it like this. These are the values that I can have in a register. I know it, it's already found. The values here are the values that are coming in over time. So if that's the case, then when I have this sample here, I know the whole left column, I can perform incremental calculations as we keep adding new data. And you won't be able to, you'll be getting all this last column on the arrival of the last data. And so about the same time this cat here arrives in the corner, all of these arrive as well. So that was my sort of time model. And I said, okay, so what I can do for each of these diagonals, I can have an adder. Because it's the match filter approach where it's adding and subtracting, it saves you from having to have 19 multipliers, which is great. I chose 10 bits because my original model for my A to D converter was I thought 10-bit would cover for something in the neighborhood of around 1 megasample per second. And I wanted to have an 11th bit on it for overflow and for being able to show a sign. I happened to pick, when I was playing with the uniform value, I picked 5, and the reason that came up was I said, what if I made all of my 10-bit guys, my 32 10-bit channels have the same number of 1s and 0s, or very close. And I basically said, oh, if that's the case, then at any point in time I'm going to have pretty much about the same sum of all of them if they were a uniform distance away. So I just picked 5 as a number kind of in the middle. I also note that coming in, I don't think I'll ever have negative data. It'll always be positive or 0, where 0 probably isn't even going to occur because of noise. Anyhow, just those are some thoughts, and I wanted to sort of share this spreadsheet idea. I just use Excel, and that being the case, I guess the next thing I wanted to do was to actually take a peek at the little piece of design that I did. This is the Vivado design tool. The project currently is considered channel 1, which is a single channel, and I'm going to click on it. It's going to take some time to bring it up, but I thought you might at least sort of see what's going on when the tool is coming to life. What the tool does is it gives you the ability to create high-level chunks of code that are going to describe the functionality of your design, and it'll allow you to introduce constraints. In other words, define clock speeds. It'll allow you to define where the I/O pins are going to be. This only works for Xilinx FPGAs at this point in time. My original goal was to try and do this whole thing in Verilog. I also, for my simulations, I set neighborhood of about 10 megahertz as my sampling rate, which is probably not realistic, but I wanted to see if I had any real timing issues, so I figured if I ran it real fast and it was okay, then when you run it slower, you usually have extra slack. I want to take a quick look at the high-level picture of this thing. This is an area called the sources. I'm going to do a thing that's called open the elaborated design. For starters, let me just give you a feeling for. Okay, so what this thing is it's all written in Verilog. Verilog is fairly straightforward. I've got 3 different modules that are going to be tied together. I kept the design intentionally flexible. I don't have an A to D converter in it. I simply am going to be using a simulator to create values that I'll apply to the input. I'm also going to have 3 different clocks on it. The reason I kept the clocks separate was simply because of I don't know what the real timing is going to be yet with the A to D converter, and having them separate lets me completely control them with simulation. It's going to turn out that when I run the simulation, I'm going to define the clocks to be matching, but and I get results coming out with that, but I don't know when we actually tie an A to D converter in how I'm going to need to tweak it. So this gives me the ability to tune it and modify the design moving forward. So this is a fat design in the sense that it has 19 accumulators, each one calculating one of those correlation elements. I'm reluctant to use the term coefficient because my son's a statistician and he goes nuclear. Anyway, this has a high-level text diagram that's going to be tying the pieces together. There is a module in the design that's called Target Out, and it's a 10-bit thingamajig which is put in there. Basically, the way FPGA design software works is if you tie something to an output, it will keep it in the design. If you had these correlation values just landing in the middle of the FPGA somewhere, then they basically would say, hey, those don't go anywhere, trim them out. So you need to make them go somewhere. So I put a multiplexed structure on this. Actually, it's not target, it's the result that I have going out as a multiplex. Target is the name of the shift register, which is going to have the 10 values in it. Here's the 19 accumulators, sort of just described. All this text that's in here is each one's just defining little blocks that are going to do the stuff. We can go over this if you want to get into the details as time progresses, but all of these things are sitting in here. And this is the high-level module. It actually presents for you a picture where you say, here's your high-level module, and in the same directory it's going to have all the little pieces. So there's going to be an output mux, which is the thing I was talking about. I used a kind of a weird approach to managing the adders, the accumulators, if you will. I noted that for capturing the results of one swing at a channel, I needed to take 10 samples. And that being the case, I wanted to have a free-running clock that would be driven to all the adders for the samples. However, if you remember the very first one that came out when the target column looked at data item 1, it produced a result, and then it didn't produce any more. So what I had to do there was say that guy needs to only have its input open at the first clock, and the next one's going to be open for 2 clocks. And as they come sliding out the bottom of that spreadsheet, each one will be open for a different number of clocks. And so I made a little circuit there that will just allow each individual adder, I keep calling an adder an accumulator, each one is going to be only open for the number of clocks when it's doing its calculation. The one on the diagonal, the one that goes, combines all inputs with all target bits, that one actually is pretty much open throughout the whole process. So that could be of use. Anyway, I'm just sort of describing some things. Sorry, I'm probably confusing the hell out of you. As they say, a picture's worth 1,024 words. I'm going to say to open the elaboration, which is going to give me, it's taking the design and translating it into building blocks inside an FPGA, the design being the text. And what this step is going to do is give me the ability to present a block diagram. And the block diagram will kind of give you some orientation. My brain kind of works better with pictures. I don't know why, but it does. I'm kind of talking over this while it's running just to make stuff up. So this is the schematic, as they call it, and I'm going to float that and make it bigger. It's not going to help too much because it's kind of complicated. But if you look at it, you'll see, I think this guy here, if I put this, see, is it going to let me know what that is? So that's the channel clock enables. This is the circuit that basically tunes which particular accumulator gets to have a clock. These things over here, see if I can get that to pop up, or at least on this corner. There should be 19 of them. These would be the accumulators. So here's number 0. Hopefully down here is 19. Yeah. See, when I put it on here correctly, it displays instance 19 of an accumulator. I suspect that this is my target, but I don't know. Yeah, this is the shift register, which is a 10-bit shifter. It's got an enable and so forth. And then this is that circuit I was mentioning earlier that I had to put on it, which is just to keep the software from basically saying these outputs here don't go anywhere, so pull them out. This thing here is going to be tied to some pins, and it basically is just there as we need to look at it. If we were to have to add a microprocessor or something like that to this, which is easy to do, we could basically have this all going to the microprocessor so it could read the individual accumulator results. So this is just thrown in as a placeholder. That's this little piece here. The rest of it is pretty much the design. So I'm going to go back here. I'm going to now confuse the heck out of you by going off and running a simulation. The simulation is, I'm going to say behavioral. All that means is I'm going to be looking at some results of this circuit when presented with some inputs that are related to those spreadsheets that I showed you. It takes a while for the simulation to run. If you want to know where the data is for that, for the simulation input, I've got that in here as well. I just wanted to give you a feeling and try and make the big picture start to come clear. As we look at this closer, I find that I can make my results vary a little bit by modifying where the clock enables go to the various accumulators. I've occasionally had too many clocks go to something, that sort of a thing. This is a snapshot of the waveforms of it. I'm going to make it run a little bit longer by clicking that. I'm going to float this picture. I'm going to expand it, and I'm going to move my little, what do you call this over here? Okay, so over here are the names of various signals. There's something that's called clock, something else called target clock, another one called timing. Those are all 3 different clock signals that kind of match each other. If you look at them here, here, and here, they pretty much track, except for there's a little bit extra activity on the left of this one and a little bit over here. This has to do with initializing the input registers and making sure that the value is loaded into the target clock. Each individual channel would have its own target register, so it would have to be initialized with its own 10-bit value. I happen to put a value in here, and it's loaded, and it just kind of hangs there. Anyway, down here we're looking at some of the results, and these are waveforms coming out. I screwed up at one point. I need to have accumulator 19 here where it says result 10 and it shows undefined. This is a screw up on my part, but I wanted to show you how. So like this is value 18 coming out, and it gives you a value. Here is A, which is a 1010 in binary, or adding 2 5s. A plus 5 gives you F, which is a 0, 1, 1, 1, 1, and then this one, that's 15, so this is 5, 10, 15, that would be 20, 25, 20, 15, 10, 5, 0, and then these all go negative, and that's what the leading 7 is going up the aisle here. Anyway, So the values coming out of the accumulator fairly closely track what's on the spreadsheets that I have. So I just wanted to give you a feeling for where we're at and things that need to be looked at. I had some questions, and the questions that I had, like I say, we're getting 19 resulting sums per channel. The first one and the last one, I think, don't give me much information. They just simply are plus or minus the input data. The single channel here takes up about 300 logic cells, of which there are about 200 logic cells for a given channel, and 200 times 32 is still a number in the, the 6,000 range or something like that. That's still a fairly small FPGA type part. What does the A to D speed need to be? What does the A to D width need to be? What type of receiver do I need for a given type of LED? I'm not sure what the frequencies are. Is there filtering? I'm not sure where that slit goes. I'd like to trim the number of bits. I'd like to understand the size of the, what's the range the A to D needs to be. If I had all 32 guys striking at me close up, how big would that number be in terms of value going into my amplifier? So there's a lot of little factors, but I think we've got something starting in the right direction. And I wanted to give you an update, let you feel, get a feeling for it. I don't want to overwhelm you too much. I figure I probably am. But remember, you probably know more logic than I do optics. So I just wanted to do an update. I'm hoping that your surgery goes well and that we're able to have a discussion. Anyhow, I'm going to go ahead and probably end this at this point. If you think of any questions, just kind of keep a little notepad of them, and then when I get back in town and you're in better shape, we can discuss. Okay? Anyway, good luck. I hope all goes well. I'll be back in town on April 3rd.